My name is Michał Stęchły and this is Noisy Intermediate Scale Podcast, a podcast where we'll have in-depth discussions about quantum computing industry, education and fundamentals. This is the first episode where I'd like to tell you about the job of the quantum software engineer. In particular, what are the differences from regular software engineer, what are typical things that quantum software engineers do, and what is the particular set of skills that help them to do the job. I work myself as quantum software engineer at Zapata Computing, and our main focus is on software and algorithms for quantum computers. This means that my perspective is limited and biased, and that's why I talked with several other people at similar positions in other companies to get a better overview of what quantum software engineers do across the whole field. So thanks to Will from PsiQuantum, Felix from IonQ, Antel and Fyodor from Xanadu, and Julian from IBM for giving me some perspective on their jobs. I tried to make this episode useful for various groups of people. Those who want to enter the field and would like to know what to expect. Those who already are working as quantum software engineers, so they can get some comparison how it looks like in other companies. Other quantum professionals, more focused on science, hardware, or business, so they can better understand their colleagues from the software side. And really anyone who's writing software for quantum computers. First, I would like to talk about the essence of the job. What's the role of a quantum software engineer? In my opinion, it's about bridging the gap between science and software. It's about creating tools that scientists can use in order to do their job more efficiently, better, but also about taking the ideas from scientists and transforming them into software that can be easily used by others. I think it's worth considering this job in two contexts. So one is comparing it to the job of a regular software engineer. I would like to start from the fact that I don't think there is such thing like regular software engineer, because it's not very homogeneous in job description. There are people that are writing Linux kernels, there are people that are writing mobile application, and there are people that are programming robots. And it's hard to say that all those jobs are the same. So it's a spectrum. And I think that quantum software engineers probably fall closest to scientific software engineers on this spectrum. It depends a lot on a specific case. It depends a lot on a specific project. But I would say that's from the classical world, that's the closest we can get. The other context that it's worth considering is the spectrum of jobs that are usually present in quantum computing companies. So this is also very company specific, so it might vary. But from my observations, usually from the technical point of view, there are software engineers that are just dealing with regular software projects, not necessarily involving anything scientific. Then there are quantum software engineers who are writing software that's closer to science, that's interfacing between the quantum computer and the real world. But then there are application scientists. And the role of application scientist is not mostly about writing software, but about thinking how we can use quantum computers to solve certain real-world problems. And then, of course, there are research scientists who are working, deeply on the science of quantum computing and not necessarily even bothering about thinking on real-world applications. With that being said, this is limited perspective obviously. It might be very different in very different companies. Even for me, when I was working at Board Technology, which was a very small startup, even though I was quantum software engineer, I was also working as more like application scientist. So it can vary, but I just wanted to give you perspective on where quantum software engineer falls on the spectrum of different jobs that you can encounter in quantum computing companies. Now that we know what's the purpose of a quantum software engineer, let's get into how this job feels like. What are typical things that quantum software engineers do? What are some challenges that they face? I will start from saying that roughly 80% of what most people are doing is just regular, good, old-fashioned software engineering. Only 20% is actually spent on learning or doing some new research-oriented projects. And this is pretty consistent across many people that I talked with. Another thing that's specific about this job is that you are working on really cutting-edge technology and science. And this, you can feel this basically all the time. This means that you rarely understand the whole context and all the details that go into what you're working on. Because, to be honest, no one understands everything in this field. Well, this is something, I think, different from working on similar scientific software developer positions in more mature industries, more mature fields of science, contrary to here where it's really Wild West. This also ties to another thing, that in this job there is a big focus on domain knowledge. And obviously domain knowledge means knowing quantum computing, but not only that. Often we are writing code that is used in the context of quantum chemistry applications or optimization applications, finance, machine learning. And the more you know about this particular field, the better. There are situations where you can get away with the general understanding, but sometimes you really need to dive very deep into a specific topic. So, for example, when I was helping with the research on application benchmark for fermionic simulations, I honestly didn't know much about fermionic simulations and Fermi-Hubbard model. So I learned a lot from my colleague Pierre-Luc, who explained a lot of that to me. And I think that was perfectly fine because, I had the software skills. He had all the scientific knowledge. We worked together on that and we did pretty good job. On the other hand, when I was working on creating abstractions for ansatses for variational quantum algorithms, I really needed to understand many details of how variational quantum algorithms work. What are different parts that go into that? What are different components? And that was something where, without that knowledge, I wouldn't be able to do the job. So this is different in different situations. Sometimes you just need to know the basics. Sometimes you need to sit down and study for a couple of days just to be able to, start working on something. As I already hinted at, this field is extremely collaborative. And really, given how complex machines, quantum computers are, it has to be in order to succeed. And this has two sides. So on one hand, you can learn a lot from other people, from people with backgrounds very different from yours, but with whom you're working hand in hand. On the other hand, it sometimes creates friction because you work with others who don't necessarily speak the same language. Another thing which is different from working in most software companies is that you can see a very large part of the technological stack, from hardware through control layer to network to low-level compilers to software frameworks for using quantum computers to more sophisticated algorithms. There is a lot there. And I think this is very, very exciting to be able to see how all these things across the field works and interact with each other. And the last thing I wanted to talk here about is that in this job, you really need to be very flexible and adaptable because things can change extremely fast. This is connected to the fact that this is cutting-edge science, and simply every now and then, which means every couple of months, there is a new research papers that forces us to rethink what we know about the space, what we know about particular algorithm or particular application. And it's, on one hand, it's extremely exciting, but on the other hand, well, you need to be constantly learning, and you can never rest from, reading the papers and talking with people, because things that have been new 2 years ago, sometimes right now are already well known, well studied, or even debunked. Okay, we know what's the essence of the job of the quantum software engineer. We know how this job looks like in general and feels like. So now let's get into what are the typical tasks that quantum software engineers do on a daily basis. In many companies, quantum software engineers are developing different frameworks like QSEs for IBM or Penlane for Xanadu or Orchestra for Zapata. And therefore, they just add new features to those frameworks. From my experience, some examples are adding support for symbolic parameters to the circuits, or coding some specific algorithm like CVAR cost function to QAOA, or adding support for certain data structures. Another thing is also connected with developing your frameworks, but more by not reinventing the wheel. So there are a lot of very good frameworks, so you want to be able to utilize them. And what this means that you need to integrate those two frameworks. So in our case, it's usually working on integrating simulators with Orchestra or certain optimizers, etc. Another big thing is helping scientists with writing the code. Sometimes it's about outsourcing, writing certain code, certain algorithms, because, for example, given team is short on time and they need help from our team. Sometimes it's about doing code review and teaching scientists the best practices, or helping them use the newest features in given framework that will allow them do their job better and faster. Sometimes it's about taking the one-time scripts that they have written and figuring out how to translate them into usable software, like scalable software integrated with the framework. Given how new the field of quantum computing is, we don't really have a lot of very good abstractions. So quantum software engineers also spend a lot of time thinking how to represent certain structures, certain objects in quantum computing. In my case, that was, for example, designing the interface for the ansatzes, or designing the interface for the optimizers, or different things like this. On top of that, there is also some DevOps work. So preparing testing pipelines, setting up CI/CD system, creating Docker images, and things like this. Sometimes quantum software engineers have also opportunity to work on some research projects. Usually it's more on the execution side rather than theory, more on the implementation, running the computation and performing data analysis, but not necessarily. I think this depends heavily on one's background. Another thing that people often ask about is what type of programming languages quantum software engineers usually use. So I would say that the dominant language is Python. There is also a big fraction of people writing in C, C++. But also talking with people, I've heard they are using languages like Julia, Go, Rust, JavaScript, or Lisp. So I would say that some companies are focused solely on the Python code, while others explore many different languages. But in general, I think it's worth having this multiple languages mindset in this line of work. As I said before, this job is not very different from the traditional software engineering job. However, it has a specific set of challenges that I think are unique for the quantum computing. Most of them come from the fact that the field is very young and still evolving. And I would say that the main challenge that we face is lack of standardization. A lot of the code we're writing is very trial and error because people have not yet figured out what is the good way, what is the optimal way to perform certain actions. There are also many competing conventions between different frameworks, so it's sometimes very confusing to switch between them or write interfaces between them. And you cannot rely on standard or common abstractions because there are very few of these abstractions. And of those that there are, some are not really that good or don't cover all the cases that you need. Another thing that has, again, more to do with the substance, so the quantum computing science, is that it can be sometimes pretty confusing, especially if you don't pay attention to the details and you're not careful with your math. It's easy to make a mistake that will just propagate through all your calculations, and that is hard to track. And I have the feeling, I might be wrong here, but I have the feeling that given how young the field is, given the competing conventions, like everything that I just talked about, this problem is more apparent in quantum computing than in some other fields of science. Another issue that comes from the same reason, the field is young, is that some libraries you will be using are not very good from the software engineering standpoint. They are written by physicists that not necessarily know all the good practices. They don't necessarily know how to write good, scalable, usable software. And therefore, well, they sometimes are buggy or poorly designed. I don't say all of them are, but certainly some of them are. A second issue that comes with the software that you are using in this job, with the libraries, is that they are extremely unstable, at least some of them. The versions can change very fast, and there might be a lot of breaking changes between the versions, which means that you have to be very, very careful with the version control, that your code can get outdated in just a couple of months. And it might be really hard sometimes to run the code that you've written a year ago because it's just like so incompatible with the current library versions. A different thing that can be pretty frustrating is that the code that you have just written might be very quickly thrown away or turn out that it needs a lot of improvement because of how our understanding of the science changed. Which is not a bad thing in itself, because, as I said, we are prototyping, there's a lot of trial and error. However, if you're not prepared for that, it can be frustrating that the project that you have been working on for a couple of weeks, well, is just not relevant anymore after the newest paper came out and showed that actually this method has some issues that will render it useless. And the last challenge that I wanted to talk about is that there are not that many good places to learn about quantum software engineering. You can learn a lot about software engineering in general. You can learn a lot about the science of the quantum computing, but there are not really that many resources that talk about the challenges that I just talked about, how to deal with these challenges, what are some good practices. So you are basically on your own when it comes to education, and you need to talk with other people to just see how to solve certain problems, because there are simply not enough tutorials in the internet how to, for example, integrate simulator with certain framework or things like this. And to be honest, it also, at this stage of the development of the quantum computing software, it doesn't really make that much sense to have a lot of tutorials, because, as I said, they will become outdated pretty soon due to the rapid pace of changes in the libraries. There are also a couple of other minor issues that are not profound, but sometimes very annoying, like the fact that quantum computers are inherently random through the sampling process. It's sometimes very hard to test properly certain parts of your code. Also, some calculations might take very, very long time, and sometimes you hit performance issues when you scale up your circuits. So, for example, if you tested your code only for circuits up to 10 qubits, and then suddenly someone wants to run it on a circuit that has 25 qubits, it turns out that your code is not very good, and it has such poor performance that you cannot use it for bigger circuits. And, well, you simply need to think about performance all the time, because at some point it might just come back to you. And last but not least is that there is, especially for people who don't have background in quantum physics, there is a lot of jargon that you need to get used to. So it might be pretty tough at the beginning. So far, the things that I have talked about were rather general, but now I would like to tell you about some specific projects I've been working on, specific tasks I've been working on at Zapata, to give you a better understanding, to help you imagine how this job looks like on a daily basis. My main responsibility as a quantum software engineer at Zapata is maintaining the scientific software libraries for orchestra. And I would like to tell you about a specific project I've been recently working on. So it all started in April 2020 when I wanted to integrate the QLux simulator with orchestra. QLux is a quantum computer simulator that seems to have very good performance. So I simply wanted to add it to the simulators supported by orchestra so that anyone at Zapata can use it. It turned out that even though it wasn't very hard in general, for some reasons the XX gate didn't work. Also YY and ZZ gate as well. Given that I didn't have too much time to work on this, I just left that as it was. It wasn't very high priority, so I put that on hold. Unfortunately, I got involved in some other projects that were pretty important, so I didn't have time to actually get back to this particular task for a couple of months. And when I did finally came back to this and I wanted to fix this integration with QLAX, it was already November 2020. In order to figure out what's exactly wrong with this QLAX integration, because I didn't remember what was the issue. I only remembered it was somehow connected to the XX gate. I created a circuit and ran it using 3 different simulators. So QLAX, obviously, QVM, the simulator from Rigetti, and Qiskit simulator. But it turned out that actually all of them were giving me different results. So I didn't know which of them is actually correct. Even worse, after I started digging deeper, it turned out that all of them are giving different results not only for the XX gate, but also for some other gates. So regarding the XX gate, it turned out that different frameworks have different conventions for how you pass the parameter into the gate. In some frameworks, it's you just pass an angle. In some other, you need to divide this angle by 2 first. In some other, you have to flip the sign of the angle, which was pretty confusing, but finally I figured that out and I fixed the behavior of the QLAX integration. So it turned out that actually the QLAX and the QVM were working, and the one simulator that was not working properly was Qiskit simulator. But it's not that it wasn't working entirely. After analyzing what's wrong, it turned out that the Qiskit simulator is introducing a global phase into the results. So if you measure it, the results are correct, but if you look at the wave function, well, it looks differently. One of the fix that I tried was just updating the Qiskit version, and it helped. We were using the older version of Qiskit, and it simply was a bug there that got fixed. So it didn't took that much time to find the issue. The problem was that that was not the only difference between the Qiskit versions. So in order to fix this issue in the simulator, I had to update the code in a couple of places in our libraries to account for other changes that happened in the Qiskit in the meantime. I also wanted to be sure that this issue will not happen again in the future. So I decided that I will write tests that will make sure all simulators are working consistently and that all simulators are following the exact same conventions. And if you spend some time thinking how to do that, there are actually 2 cases you need to consider. One is for testing a simulator which is a wave function simulator, so the simulator that returns you the wave function of the quantum state. And the other is more like a sampling simulator, so the simulator that just returns you bit strings. And we decided to write 2 types of tests. One was for the wave function simulator, and the other was for the expectation values. Unfortunately, after talking with some scientists on the team, I realized that this designing tests is not as simple as it looks. Because if you want to write tests for 2-qubit gates that cover all the possibilities, it looks a lot like state tomography. And unfortunately, quantum state tomography is very, very resource intensive. And this is not something you want to use for your unit tests that you run basically anytime you introduce some changes into the code. So we sat down with my colleagues, Peter Johnson and Pierre-Luc Dallaire-Demer, and we figured out what is a good subset of the states and the operators that we want to use for tests for all the gates to make sure that the results we are getting are the correct results. After that was done, I spent hours with Pierre-Luc debugging the matrices and trying to understand how different conventions in different frameworks look like, why in one framework you have minus here and in the other you don't have, why one introduced some global phase and the other doesn't. And finally, I managed to do all that, and right now we have really nice set of tests in Orchestra, and we use this test for all the simulators so that we know that all the simulators behave exactly the same when you provide them the same parameters. How much time did all this took? Well, it took about 3-4 weeks, depending on how you count. So that was quite a lot of time. And I think it shows a couple of challenges that I mentioned before. Like, for example, quickly changing frameworks and the need for updating your code while those frameworks versions change. Also, the need for understanding the science of the problem that you are trying to solve. But also, it shows that even as a quantum software engineer who's mostly implementing the code, I had opportunity to work with the scientists to learn some new scientific concepts. And I think this is a good example that shows how collaborative this field is. Another project that I work on was about designing the ansatz interface. So interface is a structure, or you can think about it as an abstract class, which ensures that all the classes implementing given interface are compatible. In Orchestra, we use interfaces because we want our code to be scalable and modular. So if you want to change from one simulator to another or from one optimizer to another, it should really work seamlessly. So my task was to implement an interface that will allow you to test different ansatzes for the same algorithm. And ansatz, for those who don't know, is basically a parametric quantum circuit. So what I did. So first I coded a very basic prototype just to get a better feeling of what might be some issues that I will be facing. While doing that, I talked with many scientists on our team to get a better idea of what are their needs, of what are different types of ansatzes that I might not be very familiar with. And I kept iterating on this prototype, trying to find ways to implement in Python in the way that's elegant and efficient to use, but also easy to use for people who don't necessarily have very strong software background. Some challenges that we faced, were the question whether this ansatz should be implemented as part of the circuit class or whether it should be a totally separate entity. Both had, different pros and cons that we had to weigh against each other. And also how to deal with the ansatzes that have parameters which are not directly corresponding to parameters of the gates. So, for example, in QAOA, no matter how big the circuit is, how many qubits you have, you always have two parameters per layer, so beta and gamma. And they somehow translate into the parameters of the gates, but it's not one-to-one mapping. After many hours of discussions with the scientists and with other people on our team, I've managed to create this interface, and I have written tests to make sure that it behaves the way I want it to behave. And then I had to refactor existing code to work with this new interface. And it's proved to be much more difficult than I initially suspected. There were more issues here. For example, I had to introduce support for parametric circuits in a couple of places that I didn't do before. But finally, we got there and we had really nice ansatz interface in our framework. I would like to emphasize a couple of things, which this example shows. It shows that this was really a team effort, and there have been around 10 people involved in the whole process. It wasn't just me thinking what's a good way to represent ansatz as a Python class. It was really me discussing with many people. Also, this took about a month to get it right and to actually implement all of that in the code. And out of this month, actually 2 weeks we spent just thinking about the design and working on the first prototypes. And this emphasized the problem that we don't have that good abstractions in the quantum computing, and we don't necessarily know what are the best ways, to think about certain, objects like ansatz. Even though I could talk for hours about other projects I've been working on and other examples of the tasks that I have done, I think this is enough to give you the better picture of what quantum software engineers do on a daily basis. And before the end, I would like to spend a couple of minutes to summarize what are some qualities needed for this job. Now that you know how does the job of a quantum software engineer looks like, feels like, what it's all about, I would like to spend a couple of minutes to summarize what are some of the qualities that are needed for this job. And I think this can be useful both for people that are aspiring to get into the position of quantum software engineer, but also to people working in quantum computing companies, or even not quantum computing companies, but just trying to build a quantum computing team in their own company, to help them look for certain characteristics, certain skills in the people they want to hire for this position. So from the technical skills, definitely you need people who are good in software engineering. Most of the job is about writing software, and this is the main skill that you will be using in this position. However, other skills and domain knowledge definitely also can be a plus, depending on the particular needs of the team. To give you some idea what I mean by this, here are a couple of examples that I heard from people I talked with of what they found useful in their job. So these were things like knowing about computer networks, knowing the control science, knowing how the compilers work, the classical compilers as well, the optimization methods, mathematical optimization, working knowledge about machine learning, but also some basic knowledge of quantum chemistry or finance are all things that people found useful in their job at one point or another. Apart from technical skills, it's important to have some, I would call it scientific skills. And the two skills that I think are most important are a basic understanding of how science and scientific process works, and also the skill of reading scientific papers, because often you will have to implement certain algorithms that will require you to read a paper. And I think reading papers is totally separate skill from understanding how science works. It just requires practice to be able to efficiently read articles, scientific articles. There is a common misconception that in order to do this job, you need to understand how quantum mechanics works and you need to know a lot of physics, which is not true. You really need only to understand some basics, and you can definitely do a lot of progress with just understanding that. And one of the reasons for this is if you have a good team with people that are much more knowledgeable about the science part, they will simply teach you all that you need to know about it. On the other hand, knowing more science also won't hurt you, even though it might not be extremely useful on a day-to-day basis. In some situations, it will definitely make you much better fit for the task at hand. And the last group of skills that I would like to tell about, or maybe more traits, are all the non-science, non-technical human skills. And number one thing that I heard from basically all the people I talked with was curiosity. A deep, deep curiosity for how things are actually working, a passion for learning new things. This is definitely something that if you are missing, you won't feel good in this position and you won't be very effective. Because, as I said, things are changing so fast and there are so many new concepts that, well, the hunger for knowledge is really one of the most crucial elements of being, I think, working in quantum computing in general, but definitely in this position. Apart from that, as I said already a couple of times, this is a very collaborative field. And I don't think it's good to be a lone wolf quantum software engineer. I really think that you can achieve much, much more if you collaborate with others. And you have to communicate both with your team members, with people inside your company, outside of your team, who might have different background. But also you need to talk with people from the outside world who don't really know too much about quantum computing. And it's extremely useful to be a good communicator in this role. And last but not least, you need to be very flexible and very adaptive. A fixed mindset is not helpful in this job. It might turn out that you will need to learn new programming languages. It might turn out that even though you started working on compilers, you will end up working on optimizers and you will have to learn new stuff. And you cannot be a person that doesn't like changes. You need to thrive on change in order to be good in this job. If you're aspiring to be a quantum software engineer, or simply to learn more about quantum computing, here is some advice I collected from people that I talked to. First, start contributing to open source. It's a great way to learn. It's a great way to get more understanding of both how software works, but also how science works. And the maintainers of the open source project really notice people that are active in their projects from the outside. It's also a good idea to start working on a particular project and just dig deeper on this rather than trying to learn everything about quantum computing that there is. From talking with really a lot of people, it just seems to be a more efficient strategy. Many folks also mentioned to me that it's worth finding someone that's on your level of understanding that you can learn with. I personally was learning quantum computing mostly by myself. I didn't have anyone to learn with. But right now, there are many groups, many places in the internet where you can find people with similar background with whom you can help each other to learn and progress quantum computing. Don't be afraid to ask for help. As I said, the field feels very collaborative and people are usually very helpful. Many people are also very busy, so don't feel discouraged if someone is not answering your messages or your emails. Just, try asking someone else, and finally, you will definitely find someone that will help you understand the topics that you are struggling with. The last thing is a quote I really liked, which is, "The gods can bleed." Once you meet people, once you meet the top researchers in the field of quantum computing, the people that you thought have godlike intellect and abilities. And once you talk with them about the research they are working on, you will realize that they don't have all the answers. And they also are constantly learning, and they're constantly struggling to understand how these things work. And they are constantly making mistakes. So don't feel bad about the fact that you struggle with understanding certain concepts. Everyone does. And some people just spend much more time on that than the others. And now they have a better understanding and a better intuition. Thank you for listening. That's all I wanted to share with you today. I hope you've enjoyed it. Please check out the notes for this episode, as I provided links to some relevant materials that you might find interesting. And a couple of final notes. First, if you enjoyed listening to me, you might also enjoy reading my blog, Musty Thoughts. Second, I wanted to thank all the people from Twitter and LinkedIn who provided me with the questions for this episode. Third, I'm just a regular quantum software engineer, and this is the first time I've recorded a podcast by myself, so I would really appreciate getting feedback from you. You can find my email in the notes to this episode. And last, if you liked it, don't forget to subscribe so you don't miss future episodes. Have a nice day.